The terms Endian and Endianness refer to the convention used to interpret the bytes making up a data word when those bytes are stored in computer memory. In computing, memory commonly stores binary data by organizing it into 8-bit units called bytes. When reading or writing a data word consisting of multiple such units, the order of the bytes stored in memory determines the interpretation of the data word. Each memory storage location is associated with an index, called its address, which indicates its position. Bytes of a single data word are generally stored in consecutive memory addresses. Big-endian systems store the most significant byte of a word in the smallest address and the least significant byte is stored in the largest address. Little-endian systems, in contrast, store the least significant byte in the smallest address. The illustration to the right shows an example using the data word OAOBOCOD, and the four memory locations with addresses A+1, A+2 and A+3. Then, in Big-endian systems, byte OA is stored in A, OB in A+1, OC in A+2 and OD in A+3. In Little-endian systems, the order is reversed with OD stored in memory address A, OC in A+1, OB in A+2, and OA in A+3. An example on Endianness is to think of how a decimal number is written and read in place value notation. Since a number is written left to right, the leftmost position is analogous to the smallest address of memory used, and rightmost position the largest. For example, the number 123 is written 123, with the hundreds place leftmost. Anyone who reads this number also knows that the leftmost digit has the biggest place value. This is an example of a Big-Endian convention followed in daily life. The Little-endian way of writing the same number would be to put the units digit in leftmost position, 321. A person following place value notation who is not alerted of this special ordering would assume the number was 321. Endianness in computing is similar, but it applies to the ordering of bytes in memory instead of the ordering of decimal digits on paper. Both forms of Endianness are in widespread use in computing and networking. The initial Endianness design choice was mostly arbitrary, but later technology revisions and updates perpetuate the same Endianness to maintain backward compatibility. As examples, the Intel x86 processor represents a common Little-endian architecture, and IBM's Z architecture mainframes are all Big-endian processors. The designers of these two processor architectures fixed their Endiannesses in the 1960s and 1970s with their initial product introductions to the market. Big-endian is the most common convention in data networking, hence its pseudo-synonym network byte order, and Little-endian is popular among microprocessors in part due to Intel's significant historical influence on microprocessor designs. Mixed forms also exist. For instance, the ordering of bytes within a 16-bit word may differ from the ordering of 16-bit words within a 32-bit word. Such cases are sometimes referred to as mixed-endian or middle-endian. There are also some B-endian processors which can operate either in Little-endian or Big-endian mode. Endianness is important as a low-level attribute of a particular data format. Failure to account for varying Endianness across architectures when writing software code for mixed platforms and when exchanging certain types of data might lead to failures and bugs, though these issues have been understood and properly handled for many decades. Etymology. In 1726, Jonathan Swift described in his satirical novel Gulliver unregistered trademark S travels tensions in Lilliput and Blefuscu, whereas royal edict in Lilliput requires cracking open one's soft-boiled egg at the small end, inhabitants of the rival kingdom of Blefuscu crack theirs at the big end. The terms Little-endian and Endianness have a similar intent. Danny Cohen's On Holy Wars and a Plea for Peace published in 1980 ends with, Swift's point is that the difference between breaking the egg at the little end and breaking it at the big end is trivial. Therefore, he suggests, that everyone does it in his own preferred way. We agree that the difference between sending eggs with the little or the big end first is trivial, but we insist that everyone must do it in the same way, to avoid anarchy. Since the difference is trivial, we may choose either way, but a decision must be made. This trivial difference was the reason for 100 Years' War between the fictional kingdoms. It is widely assumed that Swift was either alluding to the historic War of the Roses or more likely parodying through oversimplification the religious discord in England, Ireland and Scotland brought about by the conflicts between the Roman Catholics on the one side and the Anglicans and Presbyterians on the other. Historically, byte order distinction was born out of the mainframe versus microprocessor approach. Until the 1970s, virtually all processors were Big-Endian. The first microprocessor, in the data point 2200, was designed using simpler bit serial logic where Little-endian address and data formats facilitate carry propagation. Data point's initial specification was Big-Endian, but to save transistors, they acquiesced to Intel's request for a design change to Little-endian. When byte parallel computation was implemented in later processors, Intel left in the Little-endian format as a compromise for consistency with Data Point's earlier bit serial microprocessor. Data Point never used the 8008 chip, however, and the Little-endian format was never actually necessary. The problem of dealing with data in different representations is sometimes termed the NUXI problem. This terminology alludes to the issue that a value represented by the byte string Unix on a Big-Endian system may be stored as NUXI on a PDP-11 system. Unix was one of the first systems to allow the same code to run on, and transfer data between, platforms with different internal representations. Endianness in hardware. Computer memory consists of a sequence of cells, usually bytes, and each cell has a number called its address that programs use to refer to it. If total number of bytes in memory is n, then bytes addresses would be enumerated 0 to n1. Multi-byte CPU registers are stored in memory as a simple concatenation of bytes. The simple forms are, increasing numeric significance with increasing memory addresses, known as Little-endian, and, decreasing numeric significance with increasing memory addresses, known as Big-Endian. The Intel x86 and x86-64 series of processors use the Little-endian format, and for this reason, the Little-endian format is also known as the Intel Convention. Other well-known Little-endian processor architectures are the 6502, Z80, MCS48, 8051, DEC Alpha, Ultra Nios 2, Atmel AVR, BAX, and, largely, PDP-11. The Motorola 6800 and 68K series of processors use the Big-Endian format, and for this reason, the Big-Endian format is also known as the Motorola Convention. Other well-known processors that use the Big-Endian format include the Xilinx Microblaze, Super H, IBM Power, Atmel AVR32, and System/360 and its successors such as System/370, ESA/390, and Z architecture. The PDP-10 also used Big-Endian addressing for byte-oriented instructions. SPARC historically used Big-Endian until version 9, which is B-Endian. Similarly, the ARM architecture was Little-endian before version 3 when it became B-Endian, and the PowerPC and Power architecture descendants of Power are also B-Endian. B-Endian hardware. Some architectures feature a setting which allows for switchable endianness in data segments, code segments or both. This feature can improve performance or simplify the logic of networking devices and software. The word B-Endian, when said of hardware, denotes the capability of the machine to compute or pass data in either Endian format. Many of these architectures can be switched via software to default to a specific Endian format. However, on some systems the default endianness is selected by hardware on the motherboard and cannot be changed via software. Note that the term B-Endian refers primarily to how a processor treats data accesses. Instruction accesses on a given processor may still assume a fixed endianness, even if data accesses are fully B-Endian, though this is not always the case, such as on Intel's IA64-based Titanium CPU, which allows both. Note too, that some nominally B-Endian CPUs require motherboard help to fully switch endianness. For instance, the 32-bit desktop-oriented PowerPC processors in Little-endian mode act as Little-endian from the point of view of the executing programs, but they require the motherboard to perform a 64-bit swap across all 8-byte lanes to ensure that the Little-endian view of things will apply to I/O devices. In the absence of this unusual motherboard hardware, device driver software must write to different addresses to undo the incomplete transformation and also must perform a normal byte swap. Some CPUs, such as many PowerPC processors intended for embedded use, allow per-page choice of Endianness. Floating point and Endianness. Although the ubiquitous x86 of today use Little-endian storage for all types of data, there have been a few historical machines where floating point numbers were represented in Big-Endian form while integers were represented in Little-endian form. There are old ARM processors that have half Little-endian, half Big-Endian floating point representation for double precision numbers. Both 32-bit words are stored in Little-endian like integer registers, but the most significant one first. Because there have been many floating point formats with no network standard representation for them, there is no formal standard for transferring floating point values between diverse systems. It may therefore appear strange that the widespread IEEE 754 floating point standard does not specify Endianness. Theoretically, this means that even standard IEEE floating point data written by one machine might not be readable by another. However, on modern standard computers, one may in practice safely assume that the Endianness is the same for floating point numbers as for integers, making the conversion straightforward regardless of data type. Optimization. The Little-endian system has the property that the same value can be read from memory at different lengths without using different addresses. For example, a 32-bit memory location with content 4A00000 can be read at the same address as either 8-bit, 16-bit, 24-bit, or 32-bit, all of which retain the same numeric value. Although this Little-endian property is rarely used directly by high-level programmers, it is often employed by code optimizers as well as by assembly language programmers. On the other hand, in some situations it may be useful to obtain an approximation of a multi-byte or multi-word value by reading only its most significant portion instead of a complete representation. A Big-Endian processor may read such an approximation using the same base address that would be used for the full value. Calculation order. Little-endian representation simplifies hardware in processors that add multi-byte integral values a byte at a time, such as small-scale byte addressable processors and microcontrollers. As carry propagation must start at the least significant bit, multi-byte addition can then be carried out with a monotonically incrementing address sequence, a simple operation already present in hardware. On a Big-Endian processor, its addressing unit has to be told how big the addition is going to be so that it can hop forward to the least significant byte, then count back down towards the most significant. However, high-performance processors usually perform these operations simultaneously, fetching multi-byte operands from memory as a single operation, so that the complexity of the hardware is not affected by the byte ordering. Diagram for mapping registers to memory locations. Using this chart, one can map an access from register to memory or from memory to register. To help in understanding that access, Little and Big-Endianness can be seen in the diagram as differing in their coordinate system's orientation. Big-Endianness's atomic units and memory coordinate system increases in the diagram from left to right, while Little-endianness's units increase from right to left. A simple way to remember is in Little-endian, the least significant byte goes into the lowest values slot. So in the above example, D, the least significant byte, goes into slot 0. If you were writing in a Western language the hex value 0x0AOBOCOD, you are writing the bytes from left to right, you are implicitly writing Big-Endian style. 0x0 at 0, 0xob at 1, 0xoc at 2, 0xod at 3. On the other hand, the output of memory is normally also printed out bytewise from left to right, first memory address 0, then memory address 1, then memory address 2, then memory address 3. So on a Big-Endian system, when you write a 32-bit value to an address in memory and after that output the memory, you see what you have written. However, on a Little-endian system, the logical 0 address of a value in a register is the least significant byte, the one to the right. 0xod at 0, 0xoc at 1, 0xob at 2, 0xo at 3. If you write a 32-bit register value to a memory location on a little-endian system and after that output the memory location, then the output of the memory will appear reversed. You have two choices now to synchronize the output of what you are seeing as values in registers and what you are seeing as memory. You can swap the output of the register values or you can swap the output of the memory. Because the values of registers are interpreted as numbers, which are, in Western languages, written from left to right, it is natural to use the second approach, to display the memory from right to left. The above diagram does exactly that. When visualizing memory on a little-endian system, the memory should be seen growing to the left. Examples of storing the value OAOBOCODH in memory: note that hexadecimal notation is used. To illustrate the notions, this section provides example layouts of the 32-bit number OAOBOCODH in the most common variants of Endianness. There exist several digital processors that use other formats, but these two are the most common in general processors. That is true for typical embedded systems as well as for general computer CPU(s). Most processors used in non-CPU roles in typical computers also use one of these two basic formats, although not always 32-bit. All the examples refer to the storage in memory of the value. Big-Endian. Atomic element size 8-bit, address increment 1 byte. The most significant byte value, which is OR in our example, is stored at the memory location with the lowest address. The next byte value in significance, OBH, is stored at the following memory location and so on. This is akin to left-to-right reading in hexadecimal order. Atomic element size 16-bit, the most significant atomic element stores now the value OAOBH, followed by OCODH. Little-endian. Atomic element size 8-bit, address increment 1 byte, the least significant byte value, ODH, is at the lowest address. The other bytes follow in increasing order of significance. Atomic element size 16-bit, the least significant 16-bit unit stores the value OCODH, immediately followed by OAOBH. Note that OCODH and OAOBH represent integers, not bit layouts. When organized by byte addresses increasing from right to left, visualizing memory addresses from left to right makes little-endian values appear backwards. If the addresses are written increasing towards the left instead, each individual little-endian value will appear forwards. However, strings of values or characters appear reversed instead. With 8-bit atomic elements, the least significant byte value, ODH, is at the lowest address. The other bytes follow in increasing order of significance. With 16-bit atomic elements, the least significant 16-bit unit stores the value OCODH, immediately followed by OAOBH. The display of text is reversed from the normal display of languages such as English that read from left to right. For example, the word XRAY displayed in this manner, with each character stored in an 8-bit atomic element. If pairs of characters are stored in 16-bit atomic elements, it could look even stranger. This conflict between the memory arrangements of binary data and text is intrinsic to the nature of the Little-endian Convention, but is a conflict only for languages written left to right, such as English. For right-to-left languages such as Arabic and Hebrew, there is no conflict of text with binary, and the preferred display in both cases would be with addresses increasing to the left. Middle-endian. Numerous other orderings, generically called Middle-endian or Mixed-endian, are possible. On the PDP-11 for example, the compiler stored 32-bit values with the 16-bit halves swapped from the expected Little-endian order. This ordering is known as PDP-endian, storage of a 32-bit word on a PDP-11. The ARM architecture can also produce this format when writing a 32-bit word to an address 2 bytes from a 32-bit word alignment. Segment descriptors on Intel 80386 and compatible processors keep a base 32-bit address of the segment stored in Little-endian order, but in 4 non-consecutive bytes, at relative positions 2, 3, 4 and 7 of the descriptor start. Endianness in networking. Many IETF-RFCs use the term network order, meaning the order of transmission for bits and bytes over the wire in network protocols. Among others, The historic RFC 1700 has defined its network order to be Big-Endian, though not all protocols do. The telephone network has always sent the most significant part first, the area code. Doing so allows routing to begin while a telephone number is still being keyed or dialed. The Internet Protocol defines Big-Endian as the standard network byte order used for all numeric values in the packet headers and by many higher-level protocols and file formats that are designed for use over IP. The Berkeley Socket API defines a set of functions to convert 16-bit and 32-bit integers to and from network byte order. The HTONS and HTONL functions convert 16-bit and 32-bit values respectively from machine to network order. The NTOHS and NTOHL functions convert from network to host order. These functions may be a no-op on a Big-Endian system. In CAN, multi-byte parameters are always sent least significant byte first. The same is true for Ethernet power link. While the lowest network protocols may deal with sub-byte formatting, all the layers above them usually consider the byte as their atomic unit. Endianness and files and byte swap. Endianness is a problem when a binary file created on a computer is read on another computer with different endianness. Some compilers have built-in facilities to deal with data written in other formats. For example, the Intel Fortran compiler supports the non-standard convert specifier, so a file can be opened as open unit convert equals Big-Endian or open unit convert equals Little-endian. Some compilers have options to generate code that globally enables the conversion for all file I/O operations. This allows programmers to reuse code on a system with the opposite endianness without having to modify the code itself. If the compiler does not support such conversion, the programmer needs to swap the bytes via ad hoc code. Fortran sequential unformatted files created with one endianness usually cannot be read on a system using the other endianness because Fortran usually implements a record as data preceded and succeeded by count fields, which are integers equal to the number of bytes in the data. An attempt to read such file on a system of the other endianness then results in a runtime error, because the count fields are incorrect. This problem can be avoided by writing out sequential binary files as opposed to sequential unformatted. Unicode text can optionally start with a byte order mark to signal the endianness of the file or stream. Its code point is U plus FEFF. In UTF-32 for example, a Big-Endian file should start with 0000FEFF. A Little-endian should start with FFFE0000. Application binary data formats, such as for example MATLAB MAT files, or the BIL data format, used in topography, are usually endianness independent. This is achieved by storing the data always in one fixed endianness, or carrying with the data a switch to indicate which endianness the data was written with. When reading the file, the application converts the endianness, invisibly from the user. This is the case of TIFF image files, which instructs in its header about endianness of their internal binary integers. If a file starts with a signature M, it means that integers are represented as Big-Endian, while 2 means Little-endian. Those signatures need a single 16-bit word each, and they are palindromes, so they are endianness independent. I stands for Intel and M stands for Motorola, the respective CPU providers of the IBM PC compatibles and Apple Macintosh platforms in the 1980s. Intel CPUs are Little-endian, while Motorola 680X CPUs are Big-Endian. This explicit signature allows a TIFF reader program to swap bytes if necessary when a given file was generated by a TIFF writer program running on a computer with a different endianness. Note that since the required byte swap depends on the size of the numbers stored in the file format must be known to perform endianness conversion. Bit-endianness. The terms bit-endianness and bit-level endianness often refer to the transmission order of bits over a serial medium. Usually that order is transparently managed by the hardware and is the bit-level analog of Little-endian, as in RS-232 and Ethernet. Some protocols use the opposite ordering. In networking, the order of transmission of bits is specified in the very bottom of the data link layer of the OSI model. As bit ordering is usually only relevant on a very low level, terms like LSB first and MSB first are more descriptive than the word Endianness to bit ordering. Big-Endianness is also important when handling some image file formats, especially bytonal images, which store a series of pixels as individual bits within a byte. If the bit order is incorrect, every group of 8 pixels in the image will appear backwards. Also for hardware that uses data stored in bytes, but displays individual bit on the screen. The terms bit-endianness and bit-level endianness are seldom used when talking about the representation of a stored value, as they are only meaningful for the rare computer architectures where each individual bit has a unique address. References and notes. Further reading, Danny Cohen. On Holy Wars and a Plea for Peace. IETF-IEN 137 http, www.ietf.org/IEN 137 txt. Also published at IEEE Computer, October 1981 issue. David V. James. Multiplexed Buses, The Endian Wars Continue. IEEE Micro 10, 9 doi, 10.1109/40.56322. ISNA 0272-1732. Retrieved December 20, 2008. Bertrand Blanc, Bob Mulrowy. Endianness or Where is Byte 0? Retrieved December 21, 2008. External links, Understanding Big and Little-endian Byte Order, Byte Ordering PPC, Writing Endian Independent Code and C. This article is based on material taken from the free online Dictionary of Computing prior to November 1, 2008 and incorporated under the relicensing terms of the GFDL, version 1.3 or later.